Welcome back to Applied Mathematics. In this video, we're going to look at some applications of right triangles and right triangle trigonometry. Without any further ado, let me get my head out of the way and let's dive right into it. My favorite application is the angle of elevation. And angle of elevation is an indirect way of measuring the height of something where directly measuring it by getting a ruler or a tape measure is very impractical. So I want to think about me standing over here 120 feet away from a launch pad where we're going to launch a model rocket. The rocket is going to fly up into the air in presumably a straight line, although if you've ever worked with a model rocket, you know that that's may or may not be accurate. We're going to assume that it goes straight up, it reaches a peak, and then it starts falling down. Our task is to try to figure out how high did the model rocket fly? And in order to do that, we're going to use a tool called an angle finder, which is really unfair to call it that because there are several tools that have the exact same name. But I want to think about, it kind of looks like a plastic gun, but when you pull the trigger, it allows a plumb bob to sway freely. And when you let go of the trigger, it locks into place. I unfortunately don't have one here where I'm filming the video, but I hope that you can get the idea. I guess my pen doesn't show up here. We'll use this yardstick that was just outside of my reach. But I want to sight looking down along the angle finder as I raise up and keep following until I hit the maximum point. Then I'll have a plumb bob hanging down here that's marked with a protractor, and I can use that to look at what the angle is. And so with that, I can write down the observed angle right here. I know how far away I am, and it's a fairly straightforward application of trigonometry to figure out that, oh, I have the adjacent side, I need the opposite side. 120 times the tangent of that unknown theta is going to give me my height h. So for example, if I'm using this angle finder and I find that theta is 56.8 degrees. Well, 120 times the tangent of 56.8 degrees. My calculator is very happy to tell me is 183.37, etc. 56.8 degrees is the nearest tenth of a degree, so I'd have 3 significant digits there. But I only have 2 significant digits for 120 feet, so I will round this to 2 significant digits, which is going to come out at 180 feet. Related to the angle of elevation is the angle of declination. In thinking about an application of the angle of declination, we need to be way up in the air. So I am going to very carefully draw a perfect, understandable um, uh, figure of an airplane. All right, so there's my airplane. And the airplane is, above the ground, obviously. And generally speaking, when you are flying an airplane, you know how far above the ground you are. Let's say that this airplane is flying at 5,000 feet to the nearest 100 feet. And generally speaking, when you're in an airplane, you have a good idea of which way is horizontal. And so you can look at some nice landmark on the ground, and the angle of declination is going to be the angle right here. And so the question is, if you know how high your airplane is, and you know the angle that you have to look downward in order to spot the thing that you care about, let's paint a nice target on it. How far away is that target? Well, to figure this one out, notice that because the horizontal line is generally considered parallel to the ground, if the height of the airplane is 5,000 feet, then the height over here is also 5,000 feet, and that gives us a right triangle. And if the length on the ground is our unknown, then the length up here is also our unknown. And we can see that compared to our angle, we know the opposite side, and we're trying to figure out the adjacent side. So that means that the tangent of theta is 5,000 over our unknown that I'll call x so that we have something to do. All right. So to find the length on the ground, we're going to take our altitude, which I've set at 5,000 feet for this particular problem, and we'll divide by the tangent of theta. So for example, we are flying in our airplane. We are looking down from the airplane. We see the thing of interest, and the angle downward that we have to look is 22.8 degrees. Well, my formula over here tells me I want to take 5,000. I want to divide by 22.8. I'm sorry. I want to divide by the tangent of 22.8 degrees. And my calculator is happy to tell me that that is 11,894.52, etc. My limiting factor is my altitude, 5,000 to the nearest 100th feet. So that's two significant digits. And rounding to two significant digits, I get that this is going to be 12,000 feet. These two examples certainly are not the full gamut of things that we could do trying to apply trigonometry to situations, and certainly not the only things that I might ask you about. But I wanted to go through these kind of, first of all, as an idea of how often trigonometry can show up. Right? Whenever you're talking about angles, there tends to be a nice way of getting a right angle into the picture somewhere, and then all of a sudden you have a right triangle and you can do trigonometry. I also wanted to go through these two specific examples because I do expect you to know what I mean when I say the angle of declination or the angle of um, so when I talk about the angle of elevation, I expect you to know that we are looking upward like this. When I talk about the angle of declination, I expect that you know that we are looking downward like this so that you are clear in drawing the picture which angles we're talking about. As I said, there are certainly other situations. In other situations, you are more likely to be given a figure, but those two terminologies, those two situations are things that I want you to be familiar enough with that you could draw the picture just given the description. In any event, that's all I have here, so I'll wrap this one up. I'll see you next time.